ADT and problem solving for binary tree and binary search tree. Okay, so it's unlike a linked list or array that is the linear one, but for the general tree is non-linear. So you need to learn how we can access into each node on the tree. So in tree itself, that also have some element that collected and stored in a kind of element hierarchy. So they have a top element, root one, or the parents, leaf, something like that. So that will be the name or the terminology for the tree, which is not the same as array or linked list, kind of. So for the trees, look like the tree that you guys know, right? But for the tree that we have is like going to opposite side. So it means that they're gonna have like a hierarchy, like an order. So the component of the tree we call as the node and edges, node and edges. So they will have the relationships between parents and child. So parent is the top one and child is the second layer. So it will be the relationship among the node. Okay. So in the tree, the application can be used in several ways. Like when you keep the data in the folder, you like create some storage, and then you split the folder to collect some information for that. So they will use this kind of tree to access into the informations. Okay. For the terminologies, the first one is the parents. So parents of the node n. So we can say that this will be the parents. Parents of node B is A. Okay, something like that. Child node. Child is like the node below. So B and C are child of the node A. Root is the top one. So root, there is no parents. Root, there is no parents. No parents. Age is the connection between the node and another. Subtree. So here is a subtree of A, right? The left subtree and right subtree. When it's empty, it means that no node. Okay. Leaf. So this will be leaf is like the last one, that there is no children. Okay. Internal, so not lived. Siblings is not have the common parents like DEF part. So it's the part between each node. Okay. And yeah, a center. So it's like get the parents from the node from the leaf, the height, the number of the longest part from the root to the leaf. So from the root to the leaf is called height. So that is two words. No, one is height, one is depth. Okay. So this one is from the root to the leaf is height. So here is like we would like to know the height, which is the longest part. For example, from this one, node A, 1, 2, 3. So we didn't count the node for the height, but we count the length, the longest, the part. Okay, this one is 1, 2, and 3. So it's 3 part. So the height of this tree is 3. Okay, from the root to the leaf, this is the height. And when we declare the level, we will declare as 0, 1, 2, and 3. Okay, that is two words that you need to be careful. Okay, the level is like a depth. So it starts from 0, 1, 2, and 3. It's going down, right? But height is going up. Okay, the height is going up. 1, 2, 3. 0, 1, 2, 3. So just be careful, okay? Just be careful. But once we would like to get what is the height of this one, we don't count the node, but we count this part. 1, 2, and 3. From the root to the leaf, the longest one. That will be the height of the tree. So the binary tree will shake that is the half child or and like a node or not. But when we talk about the binary tree, the word is binary. Binary means 2, right? So the precedent, and here is more than 2, so it's just a general 3, which is not covered in this class. Okay, what we're gonna start in this class is just only the binary 3, which have just only 2. Okay, 1 2 1 2 and 1 2, so it's just the binary tree. So binary tree itself, they also have its names. Okay, first is full binary tree, mean that you have the node and all leaf is full. Okay, and we can also get the height, get the number of node by the depth. So you know depth start from 0, so you can see in each level like depth 0, then 1 node, depth 2, depth 1, depth 2. So depth equal to 2, then 2 to the power of 2 is 4, and 2 to the power of 3 is 8. Okay, so we can like calculate the number of node of the full binary tree. Another one is complete. Complete mean what? When we would like to search from each level, then it's full, is filled from the left to the right. So when we search of the binary tree, it will be breadth first, for example. So we search from this one, and this one. So all is not missed. So it means that it is complete, didn't miss any value in the tree. Okay. Actually, it's not the definition of this one, but just to make sure that you understand what does the complete mean. The meanings, the definition is like, on the last level, I'll fill from the left to the right. This is the last level, I'll fill from the left to the right, fully. So it means it's complete. Even this is missed, but it's still complete because it's filled from the left to the right. Got it? But if you have this one but didn't have this line, and this one is missed, so it's not complete anymore, because you cannot, you have to skip this one and search to this one, so it's not complete anymore. So it's not fully filled from the left to the right. Got it? Balance. So here, same thing, so we can like get the balance value at each point, that the left and the right, the height is balanced, for example at this position. So it's just 1 and 2, so it's 1 minus 2 put at absolute, so it's just 1, right? But here is 1 and how many? 1 2 3 4 5. 1 minus 5 is 4, so it's imbalanced. Okay, so here's just showing you how it just look like for all of this. Is just binary tree with split by 2, all by 2, full and perfect, so all have to be completely filled. Complete is just like from the left to the right is complete, or you have this and this one. This is also complete, even this one is missed. Okay, balance is like the height of the left subtree and the right subtree here, 1 and 0, so it will be 1 minus 0. Put the absolute is still less than or equal to 1, that is balanced. If it's imbalanced, so absolute 2 minus 0, so it's equal to 2, then it is imbalanced. Okay, and here is the operation that we can take for the binary tree. One is create a tree, destroy a tree, empty, get root, set root, attack left, right, left subtree, right subtree, detach left, right subtree, get left, get right, p-order, in order, post order. Here is the part that we're gonna talk about. Okay, most of the confusing parts in this lecture. Alright, so here is the example of the tree. Okay, you can see here we have tree 1, tree 2, tree 3, and tree 4, tree 5. Then how we can connect all those three together. So you can see that in the end, after you get like root data as F for A, and then get the G as the left subtree, then you get this one as T1. And then for tree 2, you get D as the root data, and then get the left subtree of tree 1 as the subtree. So this is 3, 2, right? 3, 2. Tree number 3, root data by B, and then get the left sub-tree from tree 2, which is this one, and then right sub-tree from E. So this is tree number 3. Okay. Tree number 4, so the root data is C and do nothing. So this is tree number 4. Tree number 5, so we will add A at root, and will be left sub-tree, and will be the right sub-tree. So this is to create the binary tree. So A at the root, 3, 3 as the left sub-tree, and 3, 4 as the right sub-tree. So it will become like a complete ADT binary tree here. Got it. And what we're gonna do is how we can design the recursion for the travel of the pre-order, in-order, and post-order. So let's see together how we can use the recursive one to access the pre-order, in-order, and post-order by using the left subtree and right subtree. Okay, pre-order. You need to remember that pre-order is gonna start from root, left, and right. So start from root, left, and right this way. So pre-order is going this way, root, left, and right. So here, this is the root. So this will be the one that we're gonna access, right? And then going to the left and going to the right. So it's going to the left subtree and going to the right subtree. And then again, now we add 3. So this is the root and the left and the right. Okay, so it will be 3, 4, 14, and 10. And then after we finish the root here, to the left here, and then we're going to the right, and we will access the value from the root, which is 12, root, and left, 8, and right is 14. Here is typo error, so it's supposed to be 14 here. Got it? So we will access from the root and the left and the right. Left can represent as the left subtree and the right subtree. In the left subtree, we also access from the root, left, and right as well. From the root, left, and right. If the left subtree and right subtree have their own left subtree and right subtree here, again, we're going to access from the root, left, and right. Root, left, and right. So this is how recursive work. Okay. So it's going to be like get data, get left, and get right from the root. Second one is pre-order. Pre-order is, okay, this is still the first one, is root, left, and right, but here is some imbalance value. So let's see how it's work. Root is 10 and left, so it will be the left subtree and the right subtree here, right? So this will become the root, and this will be the left, and this become the right. And then inside here is the root. So we sit 29, right? Root, so it start with 3, and left is 14, and right is blank value. Then root, left, and going to the right, 12. So we're coming like this. And going to this one, supposed to the left and right here. So it will be 10, 29, 3, 14, 12, and 44. And the next one is after you visit root, left subtree, and then we're going to access the right subtree. So here it will be the root, and here is the left, and here is the right. So we visit root and left, and then right. And then root is 8, so it will be 10, 5, 8, and then visit root, left, and right. Okay, so it will follow this like 5, 8, 35, 9, and 17. Got it? So this will be like going to access from the left subtree, right subtree, and the subtree of each subtree. Maybe you need some time to understand this one. The second one is in order. For in order, we're gonna start from left, root, and right. Left, root, and right. So it's going this way. Left, root, and right. So it's going this way, okay? So what we're gonna do is will be the left. So for example, here is the root, this is left and this is right, and then gonna start from the left, and then here is root, this is left, this is right. So left 14, 3, 10, this is left, and 29, and here is start from 8, root, 12, and 44. Got it? Left, root, and right. Okay, same thing, just gonna start from the left, and then root and right, and this is left sub 3, and then go to the root, and here is left 8, root 5, and right start from 9, left, root, right. Okay, the post order is to be left, right, and root, so it's going this way, left, right, and root. So for this one is going to go from 14, 10, and 3. Okay, so it's left, and then we'll not go to root, it's gonna go to 8, okay, and right, and root, and the last one is root. So this will be 14, 10, 3, 8, 44, 12, and 29. Okay, same here. So it's going to be the left. So it's this one, left, root. There is no right, then going back to the root, left. Okay, and then go to the right first. So it's this way. But they were going to the root first, and then going to the right first and going back to the root as last. And then we'll not go to 10, but we come here, right, for the right. And here is the left sub 3. So we visit 8, and then after that we're gonna visit the right sub 3 first. So 9, and then 17, and going to the root, and going back to the root, and going back to the last one, you visit 10. So this is post order. Okay, so you can try on this one. And then we can also use this to solve the problem of the infit, prefit, and postfit as well by using the 3. Here is an example by using LA based on the binary tree. Okay, you can use LA to collect the information of the tree. For example, this is the index value, and you know that for the binary tree, they're gonna search as a breadth first search like this. So you can see the index is start from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to 14. So each index is gonna have the value like 15, 25, 75, and no value will put at now. Say 37, 62, 84, like this. So this is how we collect the LA base in a binary tree. Okay, but again, I think you guys know the drawback of this one, that the allocate the space. Somehow we can also use the -1 to solve some problem like this. If you miss some value, then you can declare the left and the right choice and set the root as well, and you can also get the number of free node that we have. If there is no value, they can connect to the -1. Okay, and then like for Jane, you can also that is this like connect to 1 and 2, 1 and 2. Bob connect to the 3 and 4, something like that. So you can also use this one to like set the connection of the 3 by the node, set the left and the right child. Okay, and this one is just represent how we can add the left and right sub 3 and how we can get the value. So here is the equation actually. Get left and get right, and also get the parents one. So if you know the precision of the binary search tree, then we can be able to calculate the number of the parent and child of it. Okay, here is the equations. So like when you insert the value in the tree and then you would like to get left and get right value, and you would like to insert the value and you would like to know what is the position, then you can get from the parents value. When you know the parents, then you will like know where to put the new position, or if you have the current position, then you can trace back to the parents. You can also use the pointer based for the tree as well. Just create the node and then point left and right to the node. Okay. And this is the infit, prefit, and postfit expression using tree. So here, if you have this one, then you can also use this to like express the equation. Start from the last one, like 5 plus 9, and multiply by 2, and then plus 3. So this will be the representative of this one for the binary tree. And then if you can be able to draw this tree, then you can also trace back to the infit, prefit, and postfit based on the visit of it, like left, right, root like left, something like that. Then you will get like the value of the infit, prefit, and postfit. If you go back to this one, and then you follow this protocol of prefit, postfit, then you will be able to trace back. Okay, let's see a little bit together, like in order. In order, then you're like, what are we gonna do? In order, so we will like print left subtree first, and then print the root second, and print the right subtree last. So this will be a plus h divided by m minus y. So this will be in order. Okay, in order mean the operation is in between. Pre-order is mean the operation is in the front. So pre-order, we're gonna start from the root one, right? Root and left and right. Root, left, right, then root, left, right. So plus and ah minus and my. Root, left and right. Root, left, right. Okay. Post order is will be left, right, root. Okay. Left, right, root, left, right, root, and root. So ah plus my minus, and the last one is slash here. Okay, that's all for this one.